Hi. The classical filter transfer functions were developed in terms of the Laplace transform for simplicity. But for mathematical convenience, we want to learn how to transfer these transfer functions from S domain to Z domain. There are many methods as forwarding, differencing, backward differencing, and bilinear transform. In this video, we are going to focus on bilinear transform because it's the most common method used to do this job. First, let's assume that we have a system integrator and the transfer function is equal h of s. So the signal input x of t, let's say that it's equal to the y dot, the first derivative of y of t, and the output is y of t. So the output actually will be equal to the integration of x of t dt. So if you do it in Laplace, it will be h of s equal to 1 of s. That represent the integrator, and the input x of s and the output y of s. So you can say h of s is the transfer function of the system, which is the integrator, equal the output over the input, which simply is equal 1 over s. That will help us how to find the bilinear transform. How we'll do that? We know already that the output is equal to the integrator or integration of x of t. So if you have the signal x of t, sketch against the time t, and this point it's equal to n minus 1 t, and the second point nt, and t is the sampling period. So simply you have two samples, one at nt and the one before it n minus 1 t. Like you can say, for example, you have 4t and you have 3t, something like that. And then the difference between this sample and the sample is the sampling period t. The value of the function at this one will be equal to x n minus 1t. You can write it like that. And the value of this x will be x of nt. We'll just write it like that. So to have approximation, you can have, or you can connect the line here. So the integration, it's equal to the area. So actually it will be equal to the area of the trapezoid in this region. What is the area of trapezoid? This one base, the height is equal to x n minus 1, and this one on the other base is equal xn. So you get the average of it, and then multiply by the height, which is t between this point and this point. The difference is equal to t, the sampling period. So this is the area. At the same time, we know the area, it's equal to the integration, right? So when you say you want to find the output y of t with the equal to the integration, well, we'll say the integration of x of t, this function, plus the initial condition of this one. So will be y n minus 1t. So that's y at nt, at the current position, at the current sampling, will be equal to the integration plus the initial condition, as you know. All right, so y of nt, write y of n now, is equal to integration of x of t, which is equal to the area. I will just write it now. Xn minus 1 plus xn divided by 2 times t. X n minus 1 plus x of n over t times c. This is the area. Then plus the initial condition of y, which will be at the instant just before n, which will be y n minus 1. So that's the equation that we have. Let's arrange this equation in a way we have y on one side and x on the other side. So we have y of n, and you move this one to this side, minus y n minus 1 equal to t over 2, and you have x n minus 1 plus x of n. Now I will do z transform on this difference equation. So this difference equation is approximation for the differential equation that we have in the beginning and integrated here. If you do z transform, yn will go to y of z. Yn minus 1, it's shifted by 1 unit, so we're going to use the shift, time shift property, be z minus 1 multiplied by yz. When any time you find there is a shift in the time, just multiply z bar minus this number, equal to t over 2. Xn minus 1, shift again, will be xz, but before xz we have to multiply it by z minus 1, there is shift by 1, x of z. Plus xn will be just xz. Let's arrange this equation. We'll take y of z as a common factor, and you have 1 minus z1, power minus negative 1, t over 2. You will take z minus 1 plus 1 common factor, and you have x of z. Now we will find the equivalent transfer function in z, h of z, which is equal y of z, the output, divided by x of z. That will be equal t over 2, and we have this term, z minus 1 plus 1, over this term, 1 minus z minus 1. If you like to get rid of z minus 1, multiply in the top and the bottom by z, so no change will happen to it. So you have t over 2 times. When you multiply z by z minus 1, we'll have 1 plus z. You do the same thing, multiply here and here, so z plus, minus 1. That will be h of z. So that should be equivalent to our h of s that was started. Remember, h of s was 1 over s, the integration. So if you do that, so it means 1 over s is equivalent to what we got here, t over 2 z plus 1 over z minus 1. If you want to find c, just flip both sides, 2 over t, z minus 1 over z plus 1. So if you want to transfer any transfer function from s domain to z domain, all what you're supposed to do, substitute by s to 2 over t times z minus 1 over z plus 1. Let's take a simple example. Let's say we have a system, and the system is described by differential equation dy by dt plus y equal to x of t, and we need to find the system function in z domain. So let's first find the transfer function in s domain. To do that, you transfer this equation in s domain. dy by dt will be equal to sy of s. Remember, when you want to find the transfer function, you assume all initial condition equals 0. So you have only sy of s. Please go back to the properties of Laplace to check the differentiation between s times y of s. Plus y of t will be y of s, equal x of t will be equal x of s. Now we'll take y of s as a common factor. You have s plus 1 equal x of s. So what is the transfer function? H of s is equal y of s divided by x of s, which will be equal 1 over s plus 1. So this represents the transfer function in Laplace, in S domain. Now we want to transfer this to h of z. What you'll do, you will go and substitute by this equation. S equal 2 over t, z minus 1 over z plus 1. So you write h of z equal to 1 over, and this is s, you'll have it 2 over t. I replaced by the equivalent in z. I think was in the top, z minus 1, yes, divided by z plus 1, and plus 1 here. So let's just arrange this equation. We multiply the equation by t, z plus 1 on the top and the bottom. So let me make it clear here to understand. I'll multiply here by t, z plus 1, and on the bottom t, z plus 1 to get rid from here. What we get? In the top part you will have t, z plus 1, and on the bottom, when you multiply this by this, will cancel on the bottom, and you'll have only 2 z minus 1, and 1 multiplied by this, we'll have t, z plus 1. Let's simplify it. T times z will be tz plus t. On the bottom, 2z minus 2, and this one plus tz plus t. Simplify it more. Tz plus t over, you have 2z here and tz here, so you'll have 2 plus t the whole z, and the constant left, this is t, and you have minus 2. So that will be the final equation. Let's say, for example, the sampling period t was 0.1. In this case, you will have h of z equal to 0.1 z. We don't have enough space here. H of z equal 0.1 z plus t, which is 0.1, divided by 2 plus t will be 2.1 z. In the second term, t minus 2 will be 0.1 minus 2 will be minus 1.9, and that will be your equation. And you should check the pole of z by finding the roots of the denominator. So if you have 2.1 z minus 1.9 equals 0, so you have z equal to 1.9, 2.1. You have to make sure that z absolute value less than or equal 1. Why? To be stable. And obviously that's less than 1. So it will work and to reserve the stability of the system. Alright, thank you.